Good afternoon, everyone. Welcome to the talk. This is Vinícius with PEP 683, Immortal Objects, a new approach for memory management. Take it away, Vinícius.
Thank you. It's so good to be here. It's my very first time on PodCon US, and really excited, and also a bit nervous because I'm on this side of the presentation and not on your side. This presentation is called PEP 683, Immortal Objects, a new approach for memory management. A little bit about myself. My name is Vinícius Gubiani Ferreira. I work at Asion Technologies. It's a serverless edge computing company. I just recently became a tech manager at Asion. Yay. Before that, I worked for about almost 3 years as a QA team lead. And also, before that, for almost 3 years as a Python backend Django developer. Among my hobbies, I like to work on open source projects. The most amazing project that I worked on is translating the Python documentation for Brazilian Portuguese. I also love craft beer. My favorite one is Weiss. If anyone knows where to get a good Weiss beer over here, let me know. And also like to ride a bike around the park. Don't even own a bike myself. It's a rental or rented per year. So our schedule for today, we're going to talk about memory, of course. It's like in the very first slide of the presentation. We're going to go from the very basics, talk about objects, then garbage collector, how does that relate to threads and jewels. Then we're going to discuss this PEP itself, why it was actually created, the problems that they actually wanted to solve. Then some of the challenges that they faced when creating this PEP. And then we're going to check out what's next, where can this change actually help in the future. So from the very beginning, memory 101. Everything in Python we see is an object, and if you don't believe me, I'm going to quickly demonstrate by using Python itself. If we ask Python, is 42 an object, then the answer is going to be yes. And we can do pretty much the same thing for an empty list, a type such as a float, and also methods. Methods are also objects, and all other kinds of variations of methods such as anonymous functions. And even the isInstance method is also an object. So what exactly is an object anyway? And without a long explanation, it boils down to something like this. Let's say we have a variable such as a equals 50, and then we have a name such as the a, which is pointing to something. That something is actually 50. So an object in a very narrowed explanation boils down to a type, a value, and a reference count, which is how many things are actually pointing to that value. And just in case if you actually want the nightmare version of what I just explained, you can follow the link below to go to the CPython repository. But now let's take some other objects, such as a equals 50, b equals a, and then c equals 50. If we check the memory position for them with the ID method, then we're going to notice that they all have the same memory position. So what's going on over here? It turns out that Python didn't really create 3 new objects. It actually just reused an existing object and set those 3 variables pointing to the same object. So we have the reference count, just instead of 1, actually 3. And we can also confirm that by using the is operator. They're all pretty much the same object. Now let's go the other way around. Instead of trying to increment the reference count, let's try to decrement. Let's say you set a to none and b to false, then c is the very last thing that is actually pointing to the value 50. So all of them will have now different memory positions, and the reference count will be 1. In practice, it actually won't be really 1. We'll get into that in a couple of slides ahead. And going even further, let's say we actually make the reference count reach 0 by using the delete statement explicitly. Now, since there is nobody else pointing to the value 50, then the garbage collector is actually going to kick in and claim that memory back to the operating system. So garbage collector is the way that Python internally releases memory back to the operating system and kicks in one of 3 possible ways. When a variable is reassigned, when a variable goes out of scope, such as exiting a method, or when we call the delete statement explicitly. And here's some Python code that you can actually use to check out how many references you have for pretty much anything. You can also use the sys.getHalfCount code, But I actually prefer this one, even for this longer, because it actually gives you the correct value. If you use the sys get have count, it actually creates a reference and gives you the wrong number, so you actually have to decrement by 1. And I mentioned before that if you try to do that with false, none, and some other types such as lower integers, then you're probably gonna have some weird or unexpected value. And this is because the Python interpreter, when it's booting up, it sets a lot of references to these particular variables. So you get this really, really high values, like 3000 something, for example, you've tried just for the value 1. Now, let's say we actually want to speed up our code to take as much as juice as we actually can, and we have 2 ways of doing that, which are mostly using threads and processes. Threads, they are lightweight and easily share memory, and processes, on the other hand, they're very bulky and have a hard time, takes a while to start, and a hard time into sharing memory. There are also other ways, such as async I/O and distributing jobs across the network on different computers, but they mostly boil down to just these 2, threads and processes. And what's the problem of actually sharing memory with threads and sometimes processes? It is possible for the reference count field to have a bit of a mistake over there and never actually reach 0. So what's the problem with that? We have a memory leak, like this object, the memory itself, is never released to the operating system. So keep doing that for a while and your system will run out of memory, or your application may crash. Now, after this brief intro, let's talk about the PEP itself. PEP 683 was actually created by Meta inside Instagram, and they had 3 different reasons to create this PEP. They had the issues of CPU caching validation that I actually wanted to improve. They had the issues of data races condition that they wanted to avoid as best as possible. And they also had the issues about copy on write, or just CAL for the short naming that I found online, that they also wanted to avoid. Let's discuss each one of them individually. So caching validation. In order to improve performance, the CPU actually likes to cache data that is working on, keep it near the CPU. But if, for any reason, let's say the reference count gets changed, then that memory is invalidated and the CPU needs to go again to the main memory, to the SSD, the hard drive, etc., just to fetch that object again and keep it once again near the cache memory. But for object that doesn't change throughout the whole execution of the program, this is actually a big problem because it is invalidating the CPU cache a while when it shouldn't. So ends up wasting more resources than it should. It also has the issues of data races. When we share memory with 2 different threads or processes, it is possible in a scenario where the reference count actually never reaches 0. Thread is not actually Python is not actually considered thread-safe language. So this is actually what happens. Let's say we have one object that is shared with 2 different threads, and they're both done with this object, doesn't need it anymore. So they're about to release it. So the first thread comes along, decreases the reference count from 2 to 1, and then sometime later on, the second thread does pretty much the same thing, like decrease the reference count from 1 to 0. And now, since it reached 0, the garbage collector is gonna kick in, release the memory back to the operating system, so everything is fine, everyone is happy, and life will go on. Now, this sometimes may not happen quite as well expected. Let's say we have the same object, again with 2 threads, and they try to modify this object at the same time. So let's say the first thread is in the process of actually releasing, decrementing the reference count, but all of a sudden gets interrupted by a second thread, is put on hold. And then the second thread decreases the reference count from 2 to 1 and gives control back to the first thread. And now the first thread is not actually gonna decrement from 1 to 0, but from 2 to 1. And you can probably see the problem over here, right? It's never gonna reach 0, and this memory will cause a memory leak. Luckily for us, this doesn't happen because of our very good friend, the Jew. Not so much of a good friend, right? Nobody likes the Jew. So this solves the problem, but unfortunately makes Python not concurrent. Like we can't do real multi-core processing in Python. If we had immutable objects, like, and the reference count field didn't really change, this wouldn't be a problem. Like, it'll be bypassing this issue of thread safe. And finally, we have issues about copy on write, or just CAL, as I mentioned before. So a bit of context explaining over here. Instagram, they actually used a pre-forking web server architecture in their Python Django application. So they start their server and they start to spawn child processes. And for each child processes, they actually share a copy of the parent's memory. And they have a lot of objects that are constant. Like they're never going to change throughout the whole execution of the program. So they were actually hoping to consume less memory and don't need to care much about that. However, most operating systems, they actually work on a system which is called call, copy and write. And what exactly is that? It means that anything that you actually need to change in this memory that was shared with you, it was shared in a read-only state. So for changing this memory, you actually need to make a copy of it. That's the name, copy and write. And Instagram, they actually measured up performance, did some profiling about memory, and they found something like this. Instead of having some constant use of memory, they noticed that as long as the number of requests that are actually delegated to the child processes, the memory consumption was still going up, and the shared memory was actually going down, like instead of what they are actually expecting. So this is really kind of funny, right? Doesn't make much sense since the memory is actually constant. Does anybody really have a clue on what's going on over here? So, yes, you nailed it. That's exactly like that. So the problem is you're sharing a memory, but for any particular reason, like you just set another reference, like an variable was set to a specific object, and that changed the reference count. So unfortunately, something that was supposed to be constant didn't change throughout the whole execution of the program. It is changing. So here's a more practical example just to make sure that everybody got it. Let's say we have the same very object, which is being shared with two child processes. So they have their copy of the memory, so the reference count field is actually 2. And sometime later on, after the program started, then the first child process is actually gonna delete this memory. It doesn't need this object anymore. So the reference count field is actually gonna change from 2 to 1. And now I'm gonna ask you, did this value of this object changed? It didn't, right? It's still the very same object. Like for anybody who's coming new into IT, from JavaScript, from Java, doesn't have a clue what the garbage collector or even the GEO is, this is pretty much the same variable, like a equals 50, like we saw before. But unfortunately for us, the operating system disagreed and made a copy of this object. So that's a bummer, right? So to solve this, the engineers inside Instagram, they actually proposed to have truly immutable objects for this kind of objects that don't change at all throughout the whole execution of the program. But before we get any further into the presentation, we have to clarify something just to make sure we're on the right page. They wanted to achieve truly immutable objects, but they ended up calling it immortal objects. Why is that? Probably because the objects, they live longer than usual, the other objects, so makes sense calling them immortal. Also, maybe doesn't make any confusions with things that are said to be immutable, like strings and tuples, which, by the way, they are not. Like we just saw, the reference count field can change, so they've been lied. I lied to a lot of people. We've been lied to. Like strings and tuples can be immutable, and maybe probably because immortal objects is one hell of a name. It sounds great, say so. Now let's get to the C part of this presentation. There's not a lot of code in this presentation about C code. This is a really simplified representation in C code of what an object look like, what we saw before. We have the reference count field, the object type, and the data part is not shown over here because it's much larger, so probably wouldn't fit the whole slide in the way it will be easier to read. So what they proposed is to change the reference count field to actually set it to a specific value, a really high value, to mark it as an immortal object. And which value is that? Is that really, really high value at the top right? I'm not going to even try to pronounce that. I'm going to be ashamed over here trying to read that. But you get that value by actually setting the lower 32 bits of the reference count field. And then once you reach that value, then this is actually considered an immortal object. It wouldn't change anymore throughout the whole execution of the program. And also on line 110, this is the CPython repository. I got this part. The definition of the immortal half count constant is on line 110. Some other important things they also did. they also changed the way that the PyIncrement and PyDecrement macros actually worked for doing pretty much nothing, like if you're passing an immortal object, because they live throughout the whole execution of programs, so you don't need to worry about incrementing or decrementing the reference count field anymore. Some examples of immortal objects that I found when reading online for this presentation: none, true, false, empty string, and small integers such as -5 to 256. Those are all very recurring constants inside Python, so it actually makes sense to marking them as immortal. If you try the same code example that I showed before, you're probably going to have reference count just 1 for Python 3.12 further. And what they got after implementing this change on Python itself, they notice a decrease in memory consumption as the number of requests are actually going up, and an increase in shared memory also when the number of requests were still going up. But most important, this is like even greater than this graphs over here, for the very first time we actually have truly immutable objects that won't change ever inside when a program is actually executing. And why is that a big deal? Because they bypass the reference count field, the garbage collector, and even most important, the GIL, the global interpreter lock, doesn't mean a thing for this object. It bypasses like it's nothing, thin air. So you can share this with any threads in any process you like, and we're safe. So that's great, right? Everything is fine, everyone's happy. Not so much. Houston, we have a problem. So keep calm and carry on. They also had to worry about issues such as backwards compatibility, like ensuring your Python application wouldn't crash all of a sudden, because we're not dealing with Python code, we're actually dealing with C code into changing this. They have to worry about accidental immortality, because immortal objects, in the end, they are pretty much like a memory leak. So if you, by accident, turn an object into an immortal object, then you lose that memory until you finish your program. And how exactly do we achieve an immortal object? You just keep setting variables or any reference that you get into your code, and the reference counts start to increase. So keep doing that for a while, and eventually you will turn your Python object into an immortal object. Luckily for us, this takes about 4 to 5 computational days, so we're safe. They also had to worry about platform compatibility, which means getting this working into Linux, Mac, Windows, different compilers such as GCC, CLang, different architectures, 32, 64 bits, ARM, and different hardware also. But most importantly, also had to worry about performance degradation. You notice I mentioned about the PyIncrement and PyDecrement macros, right? That is like the hardest part in the Python code itself. If you're doing pretty much anything with Python, you are passing by that code. It's not the only part of the code that was changed, there were other parts. But they measured it up, and performance got worse by roughly around 2%, which is fairly acceptable. Like you win in memory, but lose in CPU, so it's a trade-off. And what's next after implementing this? Where this can actually be used? So I showed this graph before, I'm going to show it again. You're going to actually have a lower consumption in memory when you're actually doing parallel processing on a large scale. As long as your number of requests keep going up, then you will consume less memory. But you have immutable objects that can bypass the GIL and other stuff. There are some other PEPs that consider using immortal objects. I'm going to quickly talk a bit about them over here. It's PEP 684, was actually presented last year here at PyCon US. I recommend you check it out. It was a great presentation. And also releasing with PEP 3.13, PEP 703, making the GIL optional. So PEP 684, what's the objective of this PEP? Is actually allowing us to do multi-core processing with multi-core parallel processing with Python. And who's the guilty for that? That doesn't allow us? It is the GIL, of course. Is the GIL actually a villain? I don't think so. I at least like to think of him as like the hero that unfortunately lived long and became the villain. And why is that? Because he actually allows us for not having to care about data races condition like we saw before with threads. But unfortunately, it holds us back, doesn't allow us to do multi-core parallel processing with Python. And what this PEP actually did, it created the idea of subinterpreters. And these are like, use all the powers in threads. They're very lightweight. but are also very isolated. You can easily be sure that nothing's going to leak from one subinterpreter to another. This PEP, it created the idea of stop sharing the GIL itself, borrowed the idea of isolated interpreter execution. The number of isolated interpreter state was decreased. This is still going on even after this PEP was actually finished, and reduced the number of global variables we had spread across Python. There are over 4,000 of them. I'm not sure the official number, how many we have, but for each new release, we're actually decreasing this number. And I read about this PEP, and I found this section really amazing. How to teach this? I had to bring it over here. In addition to PyNewInterpreter, you can also use PyNewInterpreter from config. Kept reading on, and then I found this PyNewInterpreter is actually a struct in C code, and it has its own field, own GIL. If you set it to 1, then you have an isolated GIL for yourself. If you set it to false, then it's pretty much the plain old GIL we know for quite a while. And to wrap it up, PEP 703, making the GIL optional. This PEP, it creates also the same idea of some objects will live throughout the whole execution of the program, like true, false, none, which is what we've seen before. It also, yes, we will have to change the PyIncrement and PyDecrement macros for doing nothing from these immortal objects, like it's called. So you're probably wondering, oh great, this is actually going to use PEP 683, right? Turns out it's not, because this PEP has the purpose of actually making the GIL optional, but it decided to add a new field for marking these immortal objects. So it's a different bit representation. There are 3 main parts of this PEP. It's about immortalization, which is what we've been discussing for the last 20-30 minutes. It also creates the idea of deferred reference counting, which is postponing, releasing the memory using cyclical reference, which is something we're not able to discuss over here due to time. It also creates the idea of bias reference counting, which, if I got it correct, it's like saying who's the current owner, which thread owns the object right now, so it actually allows you to change it. And my thoughts about this PEP, this is commonly for everyone that read about it. There will be 2 versions of Python, one with the GIL and another one without it. It will be slower, a lot slower, at least from last time I read about it. So depending on which processor you would actually be using, it can damage your code by about 8%. So you have to measure it carefully just to see if you're actually doing the right thing, so it's worth it. There will be a lot of code, like the libraries, that will be to need recompiled to work with this GIL-less Python version. And there will be a lot of code that is not actually thread safe. Like, you trust your code? Really? Let's check it out to see if this is actually true. This is about what I had. Here's some references that I collected when assembling this presentation. I'd like to thank you so much. I have my contacts for any feedback that you'd like to give me. Thank you so much for coming. Thank you. Obrigado. Gracias. Grazie. Vielen Dank. Merci. Jeku. Arigato. Shishue. And... nope. Still can't pronounce the last one. Sorry. Thank you so much.
Thank you. We have about 5 minutes for questions. So if you have a question, please come to one of the microphones here or in the back and ask your question.
I have a question about the, just toward the last slide, you talked about a lot of thread safe, or a lot of thread unsafe code is going to turn up. Yeah. Are you aware of any, testing frameworks or environments that would stress an existing application to try to turn these up, these kind of cases up, or maybe some static code analysis that would turn them up?
That's a good question. It's hard to know for sure because we quite can't be sure of which Python code will actually be thread safe, because we rely a lot on the GIL, because we just know it is there. We know that it's actually damaging us, but we can't be really sure about our code if it is actually thread safe or not. Like, most people don't worry about that. You just execute it and be done with it. Like, I probably guess that will be something like you have to give it a shot and notice if you have troubles or not.
Okay, thank you.
Thank you. Yep, go ahead.
Yeah. For people developing Python libraries, are there any takeaways, or is it just something to kind of know is happening and hope it will make your code faster or more memory efficient in future?
For developing libraries, since you have two versions of the Python with itself, one of the GUI and another one without it, the most common thing that will occur is like you probably get feedback from people that are actually trying to use your library and notice, oh, there's no installation, what's going on, try to reach you on GitHub or any other ways. And for performance, I probably think that if your libraries are actually doing network on a large scale, like requests, a lot of stuff, there are probably going to be some benefits, but it's hard to know for sure if you're going to benefit or not. Once again, it's probably more like a test drive to see how much of a benefit it'll be, because this talk is not really about profiling itself. Profiling was something that I didn't cover. It's on the other room, I think Pablo Galinas talk about profiling.
Okay, thanks.
Thank you.
Hi, my question is about the slide that you showed with a list of specific objects that are immortal, and or more like conceptually. My understanding is that that is a fixed list that was implemented when making the Immortal Objects change. As far as you know, are there any plans or thoughts about changing what objects are immortal in future releases or making that more flexible? Or do you think that's pretty much how it will stay?
That's a good question. It's probably possible that other objects will be added to this in the C Python code. Right now, didn't collect exactly in the reference where these objects are set, but it is possible for adding new values. I think maybe open a pull request to the C Python and to see if it is possible. I think the biggest criteria for actually marking them as immortal objects is like how much often is actually used, because then you wouldn't consume more memory than is actually necessary. I think that's the basic criteria. Like things that are very, very common, so it is possible to add them to this list.
Thanks.
What do you know about any affordances to allow coders to create their own immortal objects?
Sorry, I didn't get your question. Could you repeat?
What do you know about any affordances that will be added to allow coders to create their own immortal objects?
Right now, you can actually like set your own objects as immortal. I look it up. Like you have to do that on a C level. I think pretty much like you have to make a modified version of C Python code. Maybe in the future we'll have something like a method for setting an immortal object directly on Python code itself. It is something I, at least when I was doing the presentation, couldn't find it, and checked with some other peers and read online. This is, for now at least, just directly in the C Python code. But who knows, maybe in the next release we'll get a method for marking directly, oh, this object is immortal. Even if it's something that is interesting, but you actually have to be aware that this is in the end a memory leak, right? So you have to take a really, really good care about that.
All right, thank you very much.
Thank you.